Goodness, it takes a while to finish up this example. I just wanted to get to part C of it and finish up that angle of inclination thing. Um, when we look at this problem, there is a particle moving along this function here. The x coordinates are changing at that moment. The y coordinates, as stated there, are changing at that moment. So there's nothing constant about x or y. I imagine that means if the x's and y's are changing, probably the angle is going to change too. So let's clean this up here. We have an equation. There don't appear to be any constants. We'll have to see about what happens with this. You know what? I wonder if we could simplify this in some way. Could we use an auxiliary equation to make this easier? Let's check it out. That's not a bad idea. So that's useful. Now we have it down to two different equations. But I'm going to take a few seconds to just show you what could happen. Because the next step is to then derive. What would happen if we hadn't used an auxiliary equation? What happens if we do? And how do those derivatives look a little bit different? Once we look up top, here's the original way we wrote it. And if we derived it this way, we need to use the quotient rule. If we use an auxiliary equation, we simplified this down to just x's and thetas. So the left is the same, the right might be a little bit easier. Plugging in could be problematic, but we'll see here. So it turns out we have a lot to plug in. We know dy dt, it was given to us. Dx dt we found in part A. The x coordinate was given to us, but we seem to be missing the y coordinate. You don't need to know what this graph looks like. You could, if you're given the x value, could you plug in 8 and solve for y at any given moment and realize kind of what that is? Maybe I should have used a different color. Oh well. I was going to use orange to represent this angle. Because it turns out if that point is at 8, 2, we still need to know what secant of theta is. You can do all kinds of chicaneries with your calculator. You can plug in your x and your y coordinates, and you can do an inverse cosine and find the angle, and then take cosine of that angle, and then take the reciprocal, and then square. There's all kinds of trick stuff. But wouldn't it be much easier just to use some good old SOHCAHTOA? Look, secant is the reciprocal of cosine. Cosine should be the adjacent over the hypotenuse. So if you happen to know the x and the y coordinate, I bet you could determine with a little bit of work the hypotenuse with the Pythagorean theorem. I'll say it's about the square root of 68, or when you simplify that, it is 2 times the square root of 17. Now, if cosine is the adjacent, so SOHCAHTOA, the adjacent over the hypotenuse, secant would be the hypotenuse over the adjacent. And when we take that secant value and square it, because that is secant squared, the numbers actually get a little nicer. Something like this. And here, once we plug all the numbers in, we get negative 4/17. This is very interesting. Whenever you're looking at angles for related rates, your answer is always going to be given in radians per second, the way that we do our derivatives. Ask me about this in class, or I'll bring it up at some point. Why is it always in radians per second? Well, the short answer is it's a lot easier. It's much harder in degrees, so we want to do this the easy way. I'll talk about it later. And on the other side. So you'll see that if you plug things in the other way, you get the exact same answer as you should. So just a quick summary here. If you come across a problem like part B, the distance portion of this problem, and you have too many variables, use an auxiliary equation. Sometimes it can make it simpler, but usually you'll need to.